My dear students, very warm good morning to all of you. In the previous class, we have discussed about the strained CA heterostructures. How strained heterostructures are useful for the nano devices, nanoelectronic devices to fabricate. Or what are all the importance of the CA strained structures? Or what is the strain or stress developed at the interface of the two interface of the junctions formed by two dissimilar semiconductor materials like aluminum, gallium arsenide or silicon or germanium or so. And we have seen how the active layers are grown over the silicon or silicon germanium substrate. So that how the speed of the mobility of electrons or the mobility of electron, how the mobility of electron is improved for how the device can be or how the device could be made fast. So that is the main advantage of strained structures, strained heterostructures. Today we are going to discuss about the quantum wells. Quantum wells are actually heterostructures formed by two dissimilar semiconductor materials. So quantum wells are actually heterostructures in which a thin layer of one semiconductor is sandwiched between two layers of a different semiconductor material, thereby forming a heterojunction. So quantum wells are actually heterostructures formed by a thin layer of one semiconductor which is sandwiched between two layers of different semiconductor materials so as to form a heterojunction. Here, an important requirement is that two semiconductors have different energy gaps. That is the important thing. The materials are chosen so that electrons available for conduction in the middle layer have lower energy than those in the outer layers. So, suppose if you are taking the heterojunctions formed by aluminum gallium arsenide, then quantum wells can be formed by taking aluminum gallium arsenide which is sandwiched with a gallium arsenide. That is, on either side of the gallium arsenide semiconductor material, aluminum gallium arsenide are sandwiched, or the gallium arsenide is sandwiched between aluminum gallium arsenide. Okay. So in that way, that heterostructures can be formed. And that heterostructure, when it is used or when it is actually forming a heterojunction, when it is actually formed as a heterojunction, that will exhibit the property of a two-dimensional electron system, gas system. That is a quantum well. So that is our subject of study today. So in quantum wells, the materials are chosen so that electrons available for conduction in the middle layer, in our example, the gallium arsenide layer, have lower energy E than those in the outer layer. So outer layer will be having higher energy level, and the sandwiched semiconductor, that is in the case of gallium arsenide, which has got a lower energy level. So there is a energy dip or well. That is why it is called quantum well, because we are quantized the motion of electrons in that particular well region. Follow my point. So here between a high energy band material, a low energy band material is sandwiched. So there is constructively a creation of energy dip, isn't it? Because on either side of gallium arsenide, aluminum gallium arsenide is having higher energy level, and there is a dip for gallium arsenide. So energy dip is there, and this dipping of energy, this dip of energy is considered to be a well formation. It's actually in the shape of a well. What is a well? Well is actually a dip, isn't it? It's a dip on the earth's surface. So very similar to that concept, we say that particular dip of energy level as quantum well, because the energy, the well in which the electron motion is confined within the middle layer. Within the middle layer, the electron motion within the, or which is confined its motion in the middle level by quantizing the well, by quantizing the motion of electrons in the well structure. Quantizing the well means quantization of the electrons in the well structure. Quantum well devices are often fabricated using molecular beam epitaxy. Usually the quantum well devices are devised or which are fabricated using molecular beam epitaxy that we have already discussed and we have learnt it. The most intensively studied semiconductor materials for the heterostructures are gallium arsenide, aluminium gallium arsenide, aluminium AlXGa1 minus XAS. ഇതിൻ്റെ അർത്ഥം എന്ന് വെച്ചാൽ നമ്മളെ അകത്ത് അലുമിനിയത്തിൻ്റെ എത്ര മോളിക്യൂള്, ഗാലിയത്തിൻ്റെ എത്ര മോളിക്യൂൾ ആഡ് ചെയ്യുന്നുള്ള. ജനറലി വി സേ ഗാലിയം ആർസനൈഡ്, അലുമിനിയം ഗാലിയം ആർസനൈഡ്, AlGaS. Okay, because there are so many materials coming under the group of 3 to 5 materials. There are many materials which comes under the group of 4 to 6 materials. So 4 to 6 in the table. So such materials for 3 to 5, of course, aluminum gallium arsenide, or indium gallium arsenide, gallium nitride, aluminium nitride, and in the 4 to 6 material like plumb up, that is that PBTE, terylene, germanium terylene type materials. PBS and PBTE. So such are materials coming under 3 to 5 group. 4 to 6 group, not 3 to 5. 3 to 5 are indium gallium arsenide or aluminum gallium arsenide, such type of materials. So these materials which have got that molecular structure represented with these figures. That is why AlXGa1 XAS, it has been written for aluminum gallium arsenide. But generally when we speak of the materials, semiconductor materials for the construction of heterostructures, we say that gallium arsenide, aluminum gallium arsenide, because that is the material combination, that semiconductor material combinations which are very commonly used for the fabrication of heterojunctions or quantum wells. Okay, now we have to learn modulation doped quantum well, because modulation doped FET, modulation doped devices, we have discussed about this one, but we don't know what is meant by modulation doping. So today we are going to discuss about modulation doped quantum well and what is meant by modulation doping. And what is modulation doping? Modulation doping is a technique for fabricating semiconductors such that the free charge carriers are spatially separated from the donors. Understand this principle. It's a technique for fabricating semiconductors such that the free charge carriers are spatially separated from the donors. Whoever is giving the charge carriers that are spatially separated from the charge carriers, free charge carriers are actually separated from that particular donor material, because this eliminates scattering from the donors. Why we are doing so? Because this separation of the donor material with the charge carriers, the free charge carriers, which eliminate the scattering from the donors. There are different types of scattering we have learned. When the electrons are moved at a very fast manner through the heterojunction, that is the interface, so there are so many chances of getting scattering of electrons. Different types of scattering like impurity scattering, subband, intersuband scattering, scatterings are possible. So that scattering of electrons may cause to reduce the speed of electrons in the device operation or in the device. So to eliminate such a scattering donors and hence to improve the speed of the device, we eliminate the scattering from the donors by separating, in what way? By spatially separating the charge carriers from the donors. Or charge carriers are spatially separated from donors. And that is why the modulation doped semiconductors have very high carrier mobility. That is the main advantage of using modulation doping. So I think you know the concept now. Why we go for modulation doping? Because modulation doping will always give very good speed for the device. Because in which the free charge carriers are spatially separated from the donor material from which this particular charge carriers are there. It is spatially separated. So that why the speed of the electron movement is taking place? Because since the free charge carriers are separated from the donor material, the scattering of the electrons from the donors will be eliminated. So the modulation doping will always give a very good speed to attain in the interface surface of the heterojunction. So that is why the modulation doped heterojunctions, for example, the modulation doped quantum wells, are very high speed of carrier mobility at the interface. Follow my point. Consider that we build a symmetric well by facing two aluminum gallium arsenide heterojunctions opposing each other. Let us consider the case in which we build a symmetric well by facing two aluminum gallium arsenide heterojunctions opposing each other. Okay, aluminum gallium arsenide heterojunctions are formed, which forms a well, and we consider such a fabrication. The wide gap semiconductor material is aluminum gallium arsenide that is located at the ends and the gallium arsenide in the middle. That is, gallium arsenide material is, that is a semiconductor material that is sandwiched between aluminum gallium arsenide. On either side of gallium arsenide there is aluminum gallium arsenide. So the figure shows the band diagram of aluminum gallium arsenide modulation doped quantum well, wide well, narrow well. Then we will see this one. See here the band diagram of aluminum gallium arsenide modulation doped quantum well. So figure A gives a wide well. This is a wide well. It means that there are aluminum gallium arsenide on either side, and gallium arsenide is the in between the aluminum gallium arsenide is there. So this is the band diagram. This is the energy band. This is the conduction band, and this is the valence band. See, this is not the well formation. Actually, the well formed due to the, and that well formed which actually forms with the energy band at the conduction band and valence band. That takes the shape like this. Okay. So this is the conduction band having, I told you why this is actually having a curved shape like this. Why this we have seen already, isn't it? The quantum well case we have seen. Why this curve is actually, why the heterojunction, this curve is actually having a curve like this, and here the quantum wells are formed in the form of a triangle. Quantum wells are formed like that. Okay. So this is the gallium arsenide region, and this is the aluminum gallium arsenide region. This is the conduction band, and this is the valence band. Okay, so here this electron movement will be almost same, having the almost same energy level at all the areas. See why? Because gallium arsenide is actually a dopant free material used. Okay, so this is as far as the wide band gap material is concerned. Why, or not wide band gap, wide well. Actually, here the well has got a width somewhat large, and this is the another type of band diagram for a well which has formed between the aluminum gallium arsenide and this gallium arsenide is formed as a well. But here you can see this well is having a smaller width, a very small width compared to this larger width. This is a very small width. Okay, so this is the aluminum gallium arsenide side, and this is also aluminum gallium arsenide, and this is the gallium. So this is the well formed. Okay, this is the well formed. So here this well formed has a shaped like this because this is actually a wide gap well, and here this is a narrow gap well. This wide gap well and narrow gap well has got more relevance in the operation of this device. We will see when we come across the multiple quantum wells, the gap or the well gap will be very small and there will be a small barrier also. So each well will be separated by a barrier. So we will discuss about that later. Okay. Now these are the two wells. So this is, of course we have the delta EC and all those things we have already discussed, and that is this is the valence band and this is the conduction band. So the well is formed like this. Okay. Hope you got the idea now. Okay. The quantum well structures with either high or low mobility for electrons can be fabricated by introducing a controlled amount of impurities. The quantum well structures with either high or low mobility of electrons can be fabricated. How? By controlling the amount of impurities added to the material. The double quantum well structure with high and low mobility constitutes the base of the velocity modulation transistor. So usually for transistors for which if the mobility or the velocity of operation or velocity modulation transistors or the transistors which can be operated at a very high speed, which make use of double quantum well, not a single quantum well. Single quantum well, of course, the signal frequency will be there, but signal strength will be very less. Sometimes we have to use more quantum wells. A double quantum well structure can be used for such purposes. For high and low mobility, that constitutes the base. Actually, a double quantum well with high and low mobility of the electrons, which constitute the base of velocity modulation transistors. So, in this velocity modulation transistors, the switching from the one state to other is controlled by an electric field transfers to the layers, which redistributes the amount of charged electrons and therefore the current in neither wells. So usually when two wells, double wells means there will be two quantum wells formed, and the mobility of electrons in this quantum wells has to be controlled, isn't it? Then only the speed of operation could be controlled. So that is what is discussed here. In velocity modulation transistor, the switching from one state to the other is controlled by an electric field transfers to the layers, which redistributes. Transfers to the layers means an electric field developed or which is controlled by an electric field produced transfers to the plane of the layers form, plane of the interface, or that is the plane of interface between the junction, and transfers to this layers or transfers to this interface between the layers, which can redistribute the amount of charged electrons. Already the electrons which are crossing on over this one, that is actually the inversion layers will be formed there. That inversion layer, the electrons numbers can be controlled by having this particular electric field that we have already discussed earlier. Therefore, the current in the well can also be controlled. Once the charge of electron charge motion could be controlled at the interface, of course, that can control the current also. In the MOSFET case, we have seen that one. So, velocity modulation transistors can be operated at very high frequencies. Due to this feature, the velocity modulation transistors can be operated at a very high frequencies. Okay. The signal provided by a single quantum well is usually too small to be used in the solid state device. I told you, when we use only a single well, then in such cases, when we apply a signal for what for we use this particular well structure for devices, because such well structure will be giving a very high speed operation of the device, isn't it? But if the signal which is given to the single quantum well is very small, suppose if that is the case, then what happens? The single well cannot or which cannot operate such as small signals to operate by a single quantum. It is not possible sometimes. In such cases, we cannot use such a solid state device for a single quantum. Therefore, we make use of an array of quantum wells, a number of quantum wells. Number of quantum wells. Each quantum well will be separated by a barrier. That is the number of quantum wells. That is an array of quantum wells. There will be double quantum well. There will be a quantum well array of about 10 quantum wells. sometimes 50 quantum wells array that are used in the case of photodetectors also. So it is necessary to boost the signals. In such cases, we use array of quantum wells, especially in the case of optoelectronic devices like photodetectors. And these structures are sometimes called, or these structures are called multiple quantum wells, because it is not a single quantum well. There are arrays of quantum wells which are used for improving the signals with the same with the speed of operation. So multiple quantum wells can be used in such cases, and that are all formed by several single quantum wells put together. A number of structures formed by multiple quantum wells having a number of quantum wells formed by several single quantum wells. So one quantum well will be separating with the other one with a barrier wall, for the well. Okay, if the wells for the electrons and holes are located in the same space location, the multiple quantum well is called type 1. Type 1, what we will discuss what is type 1. If the electrons and holes are located on the same space location, I told you, if it is located in the gallium arsenide, okay, it's gallium arsenide. So if the electrons and holes are located on the same space location, the multiple quantum well is called type 1. That is type 1 multiple quantum well shown here. Here, in this quantum well, this is the conduction band and this is the valence band. So every energy band diagram, we have valence band energy and the conduction band energy, right? Okay, so this is the energy axis, so this is the conduction band and this is the valence band. So if in this case, of course, the type 1, every quantum well formed has got a corresponding, that is what we have seen here. See, if the well for electrons and holes which are located on the same space location, so if it is on the same space location of the well, here we say that it's a type 1 type. If the electrons or holes which are actually located at different space locations like this, let us consider the case here. The type 2 is used when the corresponding wells are located alternatively. See here the wells formed for the materials, whether it is aluminum, gallium arsenide, whatever it is. If the quantum well formed are alternately placed like this, so here is actually type 2 multiple quantum well. This is not a single quantum well, there are array of quantum wells like this, and this is for type 1, and which the electrons and holes are actually have in the same space location. Here it is not on the same space location, which is different. So it is alternately placed, isn't it? It's alternately placed like this. So here this is the valence band and this is the conduction band. So this is alternately the electrons or holes which are placed alternately in different locations. So that's why it is not on the same location. That's why here this energy band where the quantum wells formed are like this. Okay. So you understood the that concept here. Why is it called a type 2 multiple quantum well? Here the electrons or holes which are located on not on the same space. That's why when the quantum well is formed here, also the valence band also is quantum well. So this is the so here when this is the well and this is the barrier. Here this is actually the case of this one, and this is the well. So here the electrons are see it is shown here. This is the energy of electrons here, that's shown here. This is the conduction band, this is Eg2. Here this is Eg1 and Eg2. So here it is Eg2 and this is Eg1. So that difference you have to know. Here the valence band and conduction band has a band gap of Eg1. In the case of type 2, it has got a wide band gap. In the case of type 1, it has got a low band gap between conduction and valence band. But what about that is the Eg2 in the case of type 1? The band gap between the wells and the barrier is actually wide, isn't it? Here it is less. So that difference is there. In a multiple quantum well system, it is assumed that there is no interaction between different quantum wells because the barriers separating the wells are thick enough, usually more than 10 nanometer. Usually, when multiple quantum wells are used, the barrier thickness between the wells will be more than 10 nanometers. That is the standard usually we specify, and when we manufacture multiple quantum wells, the well barrier will be about 10 nanometers in thickness. If the energy barriers between consecutive wells are thin enough, the wells will be coupled to each other by tunneling effects. That is the mean. If the well thickness with the barrier, or if the barrier between the two consecutive wells are very thin, so there are having chances to have the tunneling effect, or electrons can tunnel through the barrier. That we have seen in the case of superlattice. We will learn it. What is a superlattice? And the discrete energy level of the quantum wells are then transformed into energy bands when there is a tunneling effect through the barriers. So that may cause to produce energy bands, usually called mini bands and mini gaps. So such energy bands, mini bands, which is causes to produce, or which causes to make the device as a superlattice, a separately a very peculiar device which has got a separate band structure, or the band structure of such device could be controlled. That is superlattice. Okay, so the discrete energy levels of the quantum wells are transformed into energy bands when the barrier thickness between the consecutive quantum wells are very thin. Okay, so this particular phenomena of superlattice could be used in optoelectronics. So in optoelectronics, multiple quantum wells are used and are made of about 50 single wells, an array of 50 single quantum wells with a periodicity of about 20 nanometers, that is barrier thickness of about 20 nanometers. Thickness of well and barrier, which comes to, that is A plus B in the case of superlattice. We will see what is A and what is B. A is the well thickness and B is the barrier thickness. A plus B is the periodicity of the well, that is periodicity of the thickness of well plus barrier. If it is 20 nanometers, then if there are 50 such wells, then 50 into 20, that is 1000 nanometers, that is 1 micrometer, isn't it? So the array thickness approaches to 1 micrometer. Now it comes under the bulk material range. So the behavior of the material will be different. The band structure will be different. The material will be exhibiting a separate behavior, isn't it? So from nanometer to bulk material, like that. This value is taken as a limit in thickness. So usually 20 nanometers, that is well width plus the barrier width, is limited as 20 nanometers in multiple quantum wells. Okay, that is taken as the limit in thickness. Otherwise, what happens? Otherwise, radiation would be strongly absorbed before reaching the inner quantum wells. When the signal is reached to inner quantum wells, in the case of optoelectrons, if the radiation reaches at the well, will be strongly absorbed, so that there will be a strong absorption of the radiations in the well. So what actually, when that particular radiation reaches at the inner wells or inner quantum wells, so most of these some of the radiations will be absorbed. So that what happens when the signal strength will be reduced. When absorption takes place, what happens? Signal strength will be reduced. So the device could not be used in such case. The spectrum of the total optical signal does not necessarily coincide with that of a single quantum well. The spectrum of the total optical signal, usually this multiple quantum well features are used in the photodetectors, especially IR photodetectors. The spectrum of total optical signal does not necessarily coincide with that of a single quantum well. Strictly speaking, it should coincide with a single quantum well. But in practice, there will be always spectral changes of the optical signal which reaches in each quantum well, because the barrier thickness may not be always same throughout. There will be slight variations in the barrier thickness between the wells. Follow my point. So the spectrum of the total optical signal does not necessarily coincide with that of a single quantum well, since the thickness of each well, that is the barrier. The thickness of each well means that is the barrier between one cell, one well, that is the barrier between one well with the next consecutive well. So such a thickness of each well is not exactly the same. So this particular phenomena, that is spectral information of each, or spectral information or energy level of each well, is an indicative factor, or is considered to be an index for the uniformity in the thickness of quantum. So if you know the spectrum of the optical signals reached for all the wells in the array, and if it is coinciding with a single quantum well, of course it is well and good, because the thickness will be uniform. If the thickness of each well is different from the other, then the spectrum of the optical signal obtained, total optical signal obtained, may not coincide with that of a single quantum well. That is why this particular the breadth of the multiple quantum well energy can be used as an index for the uniformity of the thickness of the quantum well. If the thickness are all uniform, of course the spectral energy, that is the spectrum of the optical signal, that is the total optical signal, will be having the same coincidence with the single quantum well. The single quantum well ഉണ്ടാവുന്ന അതേ സിഗ്നലിന്റെ അതേ ഇതിന് കോയിൻസൈഡ് ചെയ്തിട്ടായിരിക്കും the spectrum of the total optical signal ഉണ്ടാവുക എന്നർത്ഥം. So the multiple quantum well energy is an indicative factor, that is actually considered to be an index to know the uniformity of thickness in the array of multiple quantum wells. Okay, now you understood this concept. Okay, the band structure of a typical multiple quantum well for IR photodetectors under an applied electric field is shown in the figure. What is the figure? This is the, so this is the energy. So HV, E is equal to HV, is the electric field. So that is here. So here this is the conduction band. So this is a multiple quantum well produced, multiple quantum well. So there is quantum well, this is the well, this is the barrier, this is then the well barrier, like that. So this is the band structure for multiple quantum well for IR photodetectors, and this is an example. So this you have to learn, and you have to draw this figure whenever it is asked. And here this is HV, this is the energy, which is electric field which is applied. It's under the influence of an electric field. Now the well height delta EC can be adjusted by changing the value of X in the aluminium gallium arsenide as well as the values of energy levels through the thickness of the well. So the values of energy levels can be adjusted, or the well height delta EC can be. So what is delta EC? The delta, what is meant by delta EC? What is delta EC? That is the conduction band energy, isn't it? That is the difference of conduction band energy in the well region for aluminum gallium arsenide and gallium arsenide material. So let us consider the case of aluminum gallium arsenide material. Then delta EC, that we have already seen, that can be adjusted. That energy gap can be that is in the conduction band. Of course, the energy level difference can be adjusted by changing the value of X, that is the molecular structure, that is constant of this one, that can be adjusted by adjusting the value of X, that is the addition of this impurities, or addition of, not impurities, addition of this material molecules, isn't it? The lattice structure and molecules that can be added to this one for aluminum and gallium arsenide. So that can be adjusted with the value of X as well as the values of energy levels through the thickness of the well material. So this thickness also plays an important role. I told you this thickness is also, that can also control the energy. Okay. The levels are calculated in such a way that the second level is only a little below the bottom edges of the conduction band of the wide gap material, that is aluminum gallium arsenide. That is the wide gap material, gallium arsenide is the small gap material. In addition, the semiconductor doping is chosen so that the N is equal to 1 level is full and the N is equal to 2 is empty. The semiconductor doping is chosen in such a manner that the level N is equal to 1 level is full and N is equal to 2 is empty. That is, the level 1 is full and level 2 is empty. Likewise, this doping has to be done. So that doping actually makes here this ALX GA, what I have told you here. Addition of this doping that actually makes this ALX value. This X value is actually doping this level value. The N is equal to 1 level which is full. Then N is equal to 2 which is empty. Like that, if you chose this one like this, the doping of the material, and that actually uh, uh, make the device to control the value of energy levels and the thickness of the well. Thickness of the well that actually that also makes the energy values which can be changed or controlled. Taking this consideration into account, when a photon of energy h omega equal to E2 minus E1 impinges, electron will be liberated and drift along the z-axis by the action of weak applied electric field. So, taking this consideration into account by knowing all this aluminum gallium arsenide material with this kind of lattice formation and all those things, then this particular quantum well formed is subjected to an electric field, weak electric field. Then if the photon energy is h omega, that is equal to E2 minus E1 depending upon the energy levels of the both materials, E2 minus E1. And that impinges, electrons will be liberated and drift along the z-axis. And the electrons will be liberated, that electrons will be getting liberated along the z-axis. The action of a weak applied field which actually causes this that is drift of electron in the x-axis by the action of the weak electric field, because this is object in electric field, so electrons will be getting liberated. So that is shown here, the multiple quantum wells, and you can just draw this one to explain the multiple quantum wells and the features. So with this we finish multiple quantum wells. Now of course we will see some of the multiple quantum well devices, just like infrared optical devices and such devices in the 6th module. Okay, that you will have to learn. So when you have the concept of this one here, then you can very easy to understand the concept of operation of such devices in the module 6 IR photodetectors like. Okay. So thank you very much for patiently hearing this lecture.